Hi everyone, my name is Nicolas Decavel-Bueff and I am a current student at University of San Francisco studying data science. This project I'm going to be talking, or this presentation, I'm going to be talking a little bit about my HR analytics project. In particular, say we have a scenario. You work as a recruiter for a business and your business spends time training potential new employees for this job, and after, with all the data that they amass on how much each prospective employee has trained and other information about them, can we create a model that successfully predicts if someone is currently looking for a job to help you as a recruiter better allocate your time? Now, this presentation is going to have a pretty structured approach. I'm first going to talk a little bit about the data we're looking at, my pre-processing techniques, and then I'm going to go into my model selection. Which models did I look at? Which ensembling techniques did I look at? And finally, I'm going to talk about my final model selection and some evaluation metrics I used, and I'm going to finish with some final remarks. Now, the data itself, we're dealing with a little over 19,000 observations, and this whole problem is a binary classifier. We're just predicting ones and zeros. We're predicting whether or not someone is looking for a job or whether or not they're not currently looking for a job. And our data set includes 12 total features, where only 2 of them are actually numerical. We have the City Development Index and the training hours. And the rest are a mix of categorical, whether or not they are nominal or ordinal. For example, we have some ordinal categories of years of experience, years since last job, and potentially, your education degree and the company size. Everything else here, I would largely consider a nominal category. Now, for data pre-processing, I set up these steps for at least the categorical. I clumped the nominal and ordinal groups together, primarily because I didn't see that that one-hot encoding wasn't able to capture all the information, and it didn't impact my metric by dividing the ordinal categories into their own ordinal pre-processing steps. My first step here, however, was to use a simple imputer in which I imputed the value missing. Note that a lot of people, and there's no right or wrong answer, impute maybe the most frequent instead for categorical data. This is a good method. However, both methods, mine and the one I just discussed, add an assumption to the data on the reasons why a value is missing. Now, if we know that the value is missing due to simply they forgot to put it in, then we can maybe look at most frequent. But if there is some sort of relationship between them forgetting to put in the data and our target value, then we can't simply just impute the most frequent. We're losing some interpretation. After imputing, I simply ran it through a one-hot encoder. Now, my numerical preprocessing, I used 3 steps. I used an iterative imputer, which basically imputes using machine learning, so it will learn the value of that column that's missing with the other values in the data set. And then I scaled that, and then finally I used a quantile transformer to make it into a normal distribution, because some of the models I'll be looking at actually prefer and work better when the numerical data is normal. Now, note that I'm dealing with imbalanced data. It's not a 50-50% chance that someone is looking for a job. It's only 25% chance. That means you as a recruiter, you're currently picking a random applicant out of this list, and you have only a 25% chance of actually spending your time with someone who's looking for a job. My initial method of choosing a model was using a randomized search CV with these 4 algorithms, and each of them can account for class imbalances with a class weight parameter, and I compared the best with a weighted F1 score. Now, an F1 score takes into account both recall and precision, which to us is important for our problem, because we care not only that we're reaching out to people that are actually looking for jobs, but also that we're not missing out on opportunities with good candidates by just not selecting them as someone looking for a job. And the weighted aspect is mainly because we have imbalanced data, and this gives me a better sense for it kind of weights the F1 scores of both classes. After that, I looked at 3 different techniques. I looked at voting classifier, which basically uses a set of estimators and applies soft or hard voting. Soft voting being that it looks at the confidence that each estimator has in their prediction and uses that as a way to create a final prediction. And hard voting, it simply does majority rule. Say you have 5 estimators, 3 of them say they're looking for a job and 2 of them say they're not. Then our voting classifier with a hard scoring technique will say that they are looking for a job. Now, bagging classifier, on the other hand, uses, the way I used it personally, was using one model and bagging it, essentially, showing it a subset of the data, and doing that for 11 separate models simultaneously, and then getting some sort of hard voting scheme of majority rule there. And then finally, I looked at using a stacking classifier with gradient boosting. None of these ensemble methods actually gave me my best model, though. My best model ended up being my randomized search CV. Note that I was able to maybe get a slightly better weighted F1 score with stacking and a gradient booster, but in the end, it cost too much precision and recall for me to actually consider it with just how our business problem is kind of structured around. Note that we use a balanced class weight, and we're using 4 min samples to leave. Now, what this means is it's an early stopping technique for decision trees to stop when they get to a point that splitting a node will cause it to have less than 4 observations in either leaf. In addition, we have plenty of trees, so this kind of reduces the variance and potentially increases the generality of our final model. Now, to evaluate this, we have a confusion matrix here. Confusion matrix, they throw a lot of information about you, and there's a lot of statistics that we can get off it, but here I'm only going to look at a couple. First of all, the accuracy is 79%, which is great, but it's important to note that we're dealing with imbalanced data sets, so if we were just to look at accuracy, it wouldn't tell us much about actually how our model is doing. Since our model could always predict not looking for a job, and our accuracy would be 75%. So comparing that, that bad model of always predicting 0 with this current model, we see that our current model is much, much better, way better than just a 4% increase in accuracy. In fact, if we look at other metrics like recall, where it says that 72% of the people looking for jobs, our model actually correctly predicts them as looking for a job, and our precision metrics, which states that when our model says someone is looking for a job, we're 59% accurate. Both these combined give us a pretty good sense that our model is a much better improvement than the current system. Finally, I looked quickly at feature importance, and I saw that city development was considered the most important. And I used the method of permutation importance through sklearn. And when I graphed the relationship, I saw that higher developed cities tend to have a lower percentage of people looking for jobs, and lower developed cities tend to have a higher percentage of people looking for jobs. This kind of makes sense. You can imagine a story where someone is in a city with a low development and index, and they want to get a new job in a city with a high development index in order to transition out into a better city. So thank you so much for listening to my talk. These are a couple of final next steps that could be great for furthering this project. For example, tuning new ensemble methods and hyper-tuning my current ones. Creating models that focus primarily on interpretation versus maximizing a metric. In addition, looking more into feature engineering, or maybe implementing different techniques to counteract imbalanced data, such as SMOTE for undersampling, or for oversampling, or undersampling the majority class. Thank you so much for listening to my presentation.